All right, so while the directions won't ever just say factor, this is something you would have to possibly do. And whenever it's not just something basic, such as x squared minus 9, if you recognize that and it said factor, all of you would know to split up the x squared into x times x, split up the 9 into 3 and 3, one's plus and one's minus. So that's just the normal difference of two squares. But now when we put 4s and 2 letters, then it's like, I don't know what to do. It's the same concept. It's the difference of two perfect squares. So we take the square root of the x to the 4th, x squared times x squared. We take the square root of y to the 4th. Just like the square root of 9 is 3 times 3. What times what? The same thing equals 9. What times what? The same thing equals y to the 4th. Y squared and y squared. One's plus, one's minus. Because the inside and the outside have to go away. There is no middle term. It's just the difference of two squares, not your typical trinomial that you factor. Now, x squared plus y squared. Can we do anything else with that? What can we do? All right, not on this one. When you look at it, because the sum of two squares is just the sum of two squares. There's nothing else we can simplify it. But yes, very good. The other one could go one more step further. X and x, correct. One's plus and one's minus. And then that's as far as you can go. Again, we're not going to ask you just to factor on a problem, but that's something you might have to do within a proof. One of the sides has something like this. That's the side you should manipulate because you're going to factor it. Some of you are calling like multiplying factoring. Okay, they're the complete opposite. Factoring is kind of like unmultiplying everything. Okay, so you can't say factoring is multiplying. Going back to the problem we did the other day, we had the heart plus diamond squared. We just rewrote that to heart plus diamond times heart plus diamond. We didn't do it like you didn't do anything. Okay, you just rewrote it. Here we had to figure something out. This was factoring, this was factoring. So when we write our reasons in a minute, that is called factoring. This is just called expand or rewrite, whichever word you like best. But we did not do any kind of factoring here. Like if I write 8 squared and I rewrite that as 8 times 8, I've just rewritten it as 8 times 8. I haven't done anything. Or like if I do 2 plus 3 and I change that to 3 plus 2. All I've done is rearrange or rewrite that. But if I change that to 5, then what did I do? I added those together. Okay, so when you're thinking about, earlier someone said, well, I don't know what to write. Well, what did you do? Well, I multiplied by the reciprocal, but I don't know what to write. You just told me what to do. What did you do? Think in your head, what did I just do? I multiplied by the reciprocal. That's your reason. Write that down. Or I divided fractions. That's your reason. Write it down. So now it's no different when we put a word in there. Tangent to the 4th x, that is tangent squared x, tangent squared x, cotangent squared x, cotangent squared x. One's plus and one's minus. So it's the same concept with the word. The math is the same, it's just we're adding trig to all those math things you've always learned. Just like with x squared plus y squared, we can't do anything with tangent squared plus cotangent squared unless it was an identity. Do tangent squared and cotangent squared go together? No, they don't. So there's nothing we can combine those together with. But then here, we could split this up a little bit further. Tangent x, cotangent x, cotangent x, one's plus, one's minus. And then that would be as far as you could go. So again, the reason we're showing you this is just to show you something else you can do. Factor. multiply, divide, multiply by the reciprocal, multiply by the conjugate, get a common denominator, pull out a GCF. All of those things you'll see you're starting to do over and over and over again. All right, so this first proof today, we look at that. Our first thought should be, I'm going to manipulate the right side. One side has to stay the same. You cannot move it back and forth. We're not solving anything. We are proving that one side equals the other. So you have to pick one side to manipulate. So I'm going to pick the right side. So I know I'm cosecant B. Remember, you can write your little arrow. Cosecant B is not that bad, so I'm going to write cosecant B versus putting the arrow all the way down. All right, so when I look at that, I see two terms. So my first thought is going to be, well, is there a GCF in those terms? Sine, cosine, and cotangent. There's not. So the next thing is I have a sine and a cosine. Now look over here, I have a cosecant. Cosecant deals with sine, right? It's the reciprocal of sine. So I need to keep my sines over here. So I'm going to change that cotangent to cosine over sine. So what I end up with is sine B plus cosine B times cosine B over sine B. And why did I do that? The reason I write this, so the way I write my reasons, I wrote this line using the ratio ID. That's what I did right there. Okay, I used the ratio ID. It's reciprocal. Flips it. Okay. So the ratio are only changing tangent and cotangent to sines and cosines, or sines and cosines to tangent or cotangent. Those are the only ones that follow under the ratio. All right, so now terms. Sine B is a term. These together are a term. There are not three terms here, there's just two. So this denominator, while it's a 1, we don't want to put a sign here also, because if we put a sign here also, now we have sine squared here and sine here. We put another sign, sine cubed and sine squared, we're never going to get a common denominator. So this side needs a sign for a denominator. So cosecant B, remember this is where you can either show it and not be lazy, or don't show it and be lazy, not halfway in between. You can't just randomly multiply by sign. So if I just said sine B, can I do that? No, I can't just put a sign there, but I can do sine B over sine B. That's okay. Now just multiplied by 1, that's something to do. So either don't show it at all, but if you're going to show it correctly, because if you don't show things correctly, once you mess up, you're done. Don't even look at the rest of it. You can't recover on a proof when you mess up. Other things we do in here, you can usually sometimes recover. A proof, once you've messed up, you're done. Now, if you mess up on the reason, that's one thing. You say the wrong reason, you can still keep going. But as far as the proof goes, you cannot mess up. So I'm going to go ahead and multiply. So that's sine squared B over sine B plus cosine squared B over sine B. So I did two things there. I multiplied and I got an LCD. You could just say LCD. That'd be fine. Okay, you got an LCD. LCD would be sufficient right there. And again, whether you showed that you got an LCD or you just got an LCD, either one is fine. You don't have to show getting the LCD. All right, so now I have cosecant B equals. The whole point of getting an LCD is so that I can put my numerators together, and I need to show this step right there. What did I do? I added. I did not subtract. Some people are saying subtract when they add. 1 plus 1 is not subtract. Okay? If I had 1 minus 1, I'm subtracting or adding a negative, but if I'm just adding, there's no subtracting going on right there. Now that I've combined those, I can use my Pythagorean ID to say 1 over sine B. And again, why was I able to write 1 in the place of that? That's my reason over here. Pythag ID. And now cosecant B equals cosecant B because of the reciprocal ID. So it has to be reciprocal ID right there. That is what that is. No. Oh, yeah. Yeah. So what she did is just instead of writing it here, you wrote another step right there. Absolutely, that's fine. Okay. Usually doesn't hurt to show extra steps as long as they're correct. Okay. But don't skip steps. If you have to ask yourself, do I have to show this? Just show it. These are going to take some room. If you have to get a whole piece of paper to do one problem, that just might be how it is. Some of them take time. Some of them don't take any time. On the quiz, there was one problem that took like 2 steps, and I think someone showed me 9 steps. And it was all correct, but when you look back at it, you're going to be like, why did I not just say 1? Okay? You had reciprocals. You could have said 1 plus something and then had the answer, which you didn't. They changed it to sines and cosines or reciprocals, which is fine. Worked through it, got the answer. And that just comes with practice. There is nothing wrong with a 9-step problem, doing everything correct. It could have been a 2-step problem. Now, if it has to be 9 and you do it in 2, there's probably a problem, but the other way around is just fine. All right. All right, so this factor. I just put this factor problem up to compare these two, because if I asked you to factor that top one, that is just a simple algebra 2 problem. But if I look at these 1s, minus 3, bless you, x is in the place of cosine A, minus 4x squared is in the place of cosine squared A, it's going to be the same concept. Now, hopefully you know how to guess and check, and you don't have like the trick or the rule or the box or whatever those things are called, because they don't work for trig. So you better figure out how to guess and check pretty quickly. Because this is a 1, all I have to worry about is the factors of 4 that give me a negative 3. 2 and 2 does not work, so it has to be 4x and 1x. And since it's a negative 3, the 4 is negative, and the 1x is positive. So that is called factoring. If I factor this, I change that trinomial into 2 binomials. I unmultiplied it. Okay, factoring is not the same as multiplying. It is the complete opposite. Now, the first thing to do on these problems, when you get your classwork and your homework and you come to me and say, I don't know what to start, I'm going to say, what did I say? And this is what I'm going to say again. The first thing to do on a factoring problem, how do I know it's factoring? Because I have a constant, an x, cosine A, and a squared. Constant, an x, and a squared. Constant, cosine, and a cosine squared. Same exact concept. In order to do these, this is the important word right here. That word, or the word's over here, okay? But sometimes it's not a proof. Sometimes it's just a simplify. And then that doesn't help you over there. You don't even have the right side. That tells you what all the words need to be. All the words must be cosine. So anytime you see a problem like this, it's going to be factoring, but the first thing to do is to get all the words the same. And the word that you use is the word that is not squared. Don't change these to sines and cosines, okay? If that word was cotangent, don't make it cosine over cosine. Now you have a ratio that you have to factor, and that is crazy, and it's not impossible, but it will seem impossible if you do that. So you look at that word, and everything needs to be that word. Well, we're lucky. That one already is. but this one is not. Is there a way we can change sine squared into cosine? Cosine squared, there is. 1 minus 3 cosine A minus 4 cosine squared A all over 1 minus cosine squared A. I don't want to write that the whole time, so I'm going to use my arrow method this time. And the reason I was able to change sine squared into cosine squared, like you just said, was because of the Pythagorean ID. You what? You do. It's a proof. Aren't all these proofs? Right, 1 and 2 are just like, here's a concept that you have to learn, like we've had every day. Every day we've had some kind of like concept is what you have to do. But yes, the word proof was for 2 and 3. Or 3 and 4, whatever numbers were. 4, 3 and 4, 5. That means proof. Yes, that's what that means, proof. You have an equal sign, that means proof. Yes. Thank you for clearing that up. All right, so now we have all the words the same. Sometimes you have like terms and you have to combine them. Okay, there are no like terms right now, so we don't have to worry about that. So now we can go straight into factoring. We have our constant, our unsquared, and our squared. Here, even nicer, the difference of 2 perfect squares. Again, we know the answer on these. Every time a proof, we know this is the answer. Once we get to that, we know we did it right. So, just like that 1 minus 3x minus 4x squared, I'm going to factor the exact same way. Factors of 1, those are my only choices. And these numbers are not going to be outrageous. Okay, you're not going to get double digits and triple digits and have to factor something outrageous. We'll do that later in the second semester, but not with trig. They're going to be very easy to factor. 4 right here needs to be a 3, so that's 4 cosine A, 1 cosine A. But also, since this is a proof, I always need to be looking at the right side. That tells me what one of my factors is going to be. So there's a hint to what number you're going to use. Am I going to use 2 and 2 or 4 and 1? Well, I know I have to have a 4, so that's the number I'm going to use. And the 4 needs to be negative. The 1 needs to be positive. Down here, 1 and 1. Cosine A, cosine A. 1's plus, 1's minus. That step right there was factor. Now I factored the numerator and the denominator, so sometimes people want to write factor slash factor, or sometimes earlier someone wrote factor times 2. That's fine. You don't have to tell me. If you did factoring, I don't care how many times you factored. You can write factor times 2. You can write factor slash factor, or just factor is fine. And now I divide 1 plus cosine over 1 plus cosine is 1. That's dividing. So I'm left with 1 minus 4 cosine A over 1 minus cosine A, which is equal to 1 minus 4 cosine A over 1 minus cosine A. And how did I was able to do that? Divide, correct. I divided. So remember, we do not say reduce. We do not say cancel. We do not say simplify. Okay? We say divide. If we're combining like terms, that's going to be either add or subtract.